All right, now we're going to talk about the first law of thermodynamics. And as soon as I bring the PowerPoint up, we'll get started. There we go. All right, the first law of thermodynamics. Okay. The first law of thermodynamics is an energy conservation law that relates changes in internal energy, the energy associated with the position and motion of all the molecules of a system, to energy transfers due to heat and work. The first law is universally valid, applicable to all kinds of processes, and provides a connection between the microscopic and macroscopic worlds. As mentioned earlier, there are two ways energy can be transferred between a system and its surrounding environment: by doing work, which requires a macroscopic displacement of an object through the application of a force, and by a direct exchange of energy across the system boundary, often by heat. Heat is the transfer of energy between a system and its environment due to a temperature difference, and usually occurs through radiation, conduction, and convection. For example, in the figure, hot gases and radiation impinge on the cylinder, which raises its temperature, and energy Q is transferred by conduction to the gas, where it is distributed mainly through convection. We'll take a closer look at these figures in a moment. Okay, the first law of thermodynamics. Other processes for transferring energy into a system are possible. For example, a chemical reaction or an electrical discharge. Any energy Q exchange between the system and the environment, and any work done through the expansion or compression of the system results in a change in the internal energy delta U of the system. A change in internal energy results in measurable changes in the macroscopic A change in internal energy results in measurable changes in the macroscopic variable of the system, such as the pressure, temperature, and volume. The relationship between the change in internal energy, delta U, energy Q, and the work done on the system is given by the first law of thermodynamics. If a system undergoes a change from an initial state to a final state, then the change in internal energy, delta U, is given by the equation shown, where Q is the energy exchange between the system and the environment, and W is the work done on the system. The quantity Q is positive when energy is transferred into the system, and negative when energy is removed from the system. So if we look at this equation, delta U is the change in internal energy. U final minus U initial is equal to any energy exchange Q and the work done. It's a combination of these two. Okay. Let's get back to that figure. Let's look at this figure again, which illustrates the first law for a cylinder of gas and how the system interacts with the environment. The gas cylinder contains a frictionless piston, and the block is initially at rest. Energy Q is introduced into the gas as the gas expands against the piston with constant pressure P. Until the piston hits the stop, it exerts a force on the block, which accelerates on a frictionless surface. Negative work W is done on the gas, and at the same time, positive work W, E, and V is equal to minus W is done by the gas on the block. Adding the work done on the environment, W, E, and V, to the work done on the gas, W, gives zero net work, as it must, because energy must be conserved. Looking at the equation, we can see that the internal energy of any isolated system must remain constant, so that delta U equals zero. Even when a system isn't isolated, the change in internal energy will be zero if the system goes through a cyclic process in which all the thermodynamic variables, pressure, volume, temperature, and moles of gas, return to the original values. It's important to remember that the quantities in this equation concern a system, not the effect on the system's environment through work. If the system is hot gas expanding against a piston, as in the figure, the system work W is negative because the piston can only expand at the expense of the internal energy of the gas. The work, WENV, done by the hot gas on the environment, in this case moving a piston which moves the block, is positive, but that's not the work W in our equation. Okay, in the next section, we're going to talk about work in thermodynamic processes.